6.2 Lesson 3, Antiderivative of the Reciprocal Function and Another Form of the Fundamental Theorem of Calculus. Our objective for today's lesson is given a graph of a function f, which will be the integrand in this other function g. Given a graph of a function f, you will be able to sketch the graph of the function g that is defined using a definite integral where the function f is the integrand. For the example that we will do today, our function f that's given will be f of t is equal to t squared minus 1. Sometimes you'll be given the rule for the function f. Sometimes you'll just be given the graph of the function f. So we want to be able to do these problems whether the rule for the function f is given or just the graph for the function f is given. And then from the graph of function f, you will be able to sketch the graph of function g, where g of x is equal to the definite integral of f of t with respect to t from t is equal to a to t is equal to x. So our function g would be g of x is equal to the definite integral of f of t dt from t is equal to, for our example, 0, but it could be some other constant like 1 or 2 or 3 or -1 or -2, etc. And then from 0 to x. And of course, since we know the rule for the function f, we may write the definite integral of t squared minus 1 with respect to t from t is equal to 0 to t is equal to x. So what do we want to do? We want to sketch the graph of the function g. We begin with the function f. The graph of f is here. It is a parabola. We happen to know the rule for the function f in this problem. F of t is equal to t squared minus 1. But we should be able to do these types of problems just from the graph of f, even if we don't know the rule for it. So our function g, as we've already defined, is g of x is equal to the definite integral of f of t with respect to t from t is equal to 0 to t is equal to x. And of course, we happen to know the rule for f of t, so we can replace it with t squared minus 1, but I'll just leave it as f of t in this line and write t squared minus 1 in the next line. So our objective is to sketch the graph of the function g. So how do we interpret the function g? We can interpret it as the area under the graph of the function f from t is equal to 0 to t is equal to x. And of course, its area, to be technically correct, I should say it's the area between the graph of f and the x-axis, or the horizontal axis. So if we look at, for example, g of 1, we will have the definite integral from 0 to 1 of t squared minus 1 dt. How do we interpret that graphically? Well, here is 0. I'm showing the vertical line t is equal to 0. And then, of course, we have the graph of f, and here is the vertical line t is equal to 1. So we interpret this definite integral as the area between the graph of f and the horizontal axis. In this case, we can call it the t-axis. So it's this area. That's what it represents. And because this area is below the t-axis, it will be negative area. And you can try to approximate the area of this region visually by looking at what we have here. So this is 1 unit. And what you have here is 1 square unit. That's 1 square unit. And it's below the horizontal t-axis. It's below the t-axis, so the area of that square would be -1. But we don't have all of that square. We only have a part of it. So maybe about we have 2/3 of it. So we might think that g of 1 is approximately equal to -2/3, or -0.67. Now, since we happen to know the rule for the function f, we could actually verify that analytically. So we have g of x as given, and we may use the first fundamental theorem of calculus to find an antiderivative of the integrand. And evaluate at the upper and lower limits of integration and subtract. So g of x is equal to, by the first fundamental theorem of calculus, x cubed over 3 minus x minus the antiderivative evaluated at 0, which is just 0. So I can verify that what we saw graphically is correct by using the first fundamental theorem of calculus and evaluating the function g at x is equal to 1. So g of 1 is equal to 1 cubed is 1 over 3 minus 1. 1/3 minus 3/3 is -2/3, which is, of course, what we had estimated using just the graph of f. So what we'd like to do is we'd like to sketch the graph of the function g. And to sketch the graph of the function g, you should make a table of input and output values. So we just tried what would happen if x is equal to 1. We found out that g of x would be -2/3. What if x is 2, or 3, or 4, or 0, or -1, or -2, or -3? Well, now that we happen to have an easy way to evaluate the function g, we could take advantage of that. However, I also want to emphasize that this is something that you may have to do graphically for some problems. So let's go ahead and take a look at g of 2. So here we have g of 2, and it's the upper limit of integration that has changed. So we interpret g of 2 as the area between the graph of f and the horizontal axis, the t-axis, between t is equal to 0 and t is equal to 2. So we already found the area between the graph of f and the t-axis between t is equal to 0 and t is equal to 1. So we can actually use a property of definite integrals to make our work a little bit less. So the definite integral that we have here, from 0 to 2 of t squared minus 1 with respect to t, we may write that as the definite integral from 0 to 1 of t squared minus 1 with respect to t, and we already found the value of this definite integral. And we can add to that the definite integral from 1 to 2 of t squared minus 1 with respect to t. We know this definite integral is -2/3. What about the definite integral here? The definite integral of t squared minus 1 with respect to t from t is equal to 1 to t is equal to 2. So we interpret this definite integral as the area between the graph of f and the t-axis from t is equal to 1 to t is equal to 2. So it would be, let me show you in blue, it would be, this is the line t is equal to 1, and this is the line t is equal to 2. And of course we have the graph of f, so we're talking about this area here, the area of this region. And we can try to approximate that using just our graph. So let's do that. So here we have 1 square unit. That's 2 square units. And that would be 3 square units. So clearly we're less than 3 square units for the area of the blue region. You can sort of try and put this one over here to fill the missing part. So we may have about 1 1/3. If I had to estimate visually, I might say the area of the blue region is positive 1 1/3. So let's see if we can add that to what we had found earlier for the area of the red region. So the area of the red region is negative 2/3, and I'm estimating that the area of the blue region is about 1 1/3. So negative 2/3 plus 1 1/3, which is of course 4/3. And when you add these two fractions, what do you get? You get 2/3. So it's approximately 0.67. Now that was based on just my visual observation of the area between the graph of f and the t-axis. But now we can confirm if this is close or not to the actual value of g of 2. And that is easy for us because we happen to have this. But as I'm saying, there may be some problems where you don't have a rule for f of t, and you may have to just rely on your visual approximations. But if you wanted to use this, let's find what g of 2 is. G of 2 would be 2 cubed, which is 8 over 3 minus 2. So you can write 2 as 6 over 3. So you have 8 over 3 minus 6 over 3, which is 2 over 3, and that is what we thought when we looked at the graph visually. Now we want to take a look at g of 3, which is of course the definite integral from 0 to 3 of t squared minus 1 dt. And again, we can take advantage of what we've already done by using properties of definite integrals to rewrite what we have here as the definite integral from 0 to 2 of t squared minus 1 dt. We know that to be equal to 2/3, plus the definite integral from 2 to 3 of t squared minus 1 dt. And of course, we can find that very easily by using this, but we do want to look at this graphically as well. So we already know the first definite integral here is 2/3, so we just need to find the value of the definite integral of t squared minus 1 with respect to t from t is equal to 2 to t is equal to 3. So we interpret that as the area between the graph of f and the t-axis between t is equal to 0 and t is equal to 3. So you're going to have to find the area of this region. And there's some of it that is actually not shown on my graph. But if you do that and add to that 2/3, you will get the value of g of 3. Now that you get the idea of how to do this, we'll just go ahead and rely on what we have here to find what g of 3 is. So g of 3 is going to be equal to 3 cubed is 27, 27 divided by 3 is 9, and 9 minus 3 is 6. So g of 3 is 6. So now let's take a look at what g of 0 would be. G of 0 is equal to the definite integral from 0 to 0 of t squared minus 1 with respect to t. And since the lower and upper limits of integration are equal to each other, that would just be equal to 0. What about g of negative 1? Now this is something that you have to apply properties of definite integrals for. So we have g of negative 1 is equal to the definite integral from 0 to negative 1 of t squared minus 1 with respect to t. So one thing that you should notice right away about g of negative 1 is that the upper limit of integration is actually less than the lower limit of integration. So you want to switch the limits of integration to rewrite this as the definite integral from negative 1 to 0. But when you switch the limits of integration, you have to multiply your definite integral by a factor of negative 1. So now how do we do this graphically? You're going to look at what you have here, and you're going to interpret that as the area between the graph of f and the t-axis from t is equal to negative 1 to t is equal to 0. And then after you find that area, you will multiply by negative 1. So that area is the area of this region here, which is below the t-axis. And that area would actually be negative, and it would be negative 2/3. But then you have to multiply that by negative 1, giving you positive 2/3. So g of negative 1 will be 0.67. And you can verify that by using what we have here for g of x. So g of negative 1 would be negative 1 cubed is negative 1/3 minus negative 1. Minus negative 1 or plus 1, and that would give you 2/3. So I did this on Desmos as well. So here's the function f, and here's the function g, which is defined as the definite integral of f of t with respect to t from t is equal to 0 to t is equal to x. And I used Desmos to generate this table, and you can see that it matches what we have. It matches what we found earlier for these values that we worked on. And of course, g of negative 1 is 2/3. And of course, the table has some other values. So if you want to sketch the graph of g, you have to make a table like we did, and then you have to plot points. So let's see if we can take the information from our table and plot points to get the graph of g. So we will plot these points. We have 0, 0, 1 and negative 2/3, 2 and 2/3, 3 and 6. 3 and 6 would be somewhere up there. And then we have negative 1 and 2/3. We have negative 2 and negative 2/3, negative 3 and negative 6. So with these points that I have, and the other 2 points is not going to fit on the set of axes that I have drawn here, or that I got from Desmos. So here's the graph that I have for the function g. And we do have the point 3, 6, which is somewhere up there. So this is the graph that we have for the function g. And if you look at this, it looks like the graph of a cubic function. And of course, we expect that, and we can verify that analytically, because we know how g of x is defined. It is defined to be the definite integral from 0 to x of f of t with respect to t, and we happen to know the rule for f of t. So we need to use the first fundamental theorem of calculus to find an antiderivative of the integrand and evaluate at the upper and lower limits of integration, and we get g of x is in fact a cubic function. And what we have here is the graph of g of x is equal to x cubed over 3 minus x. But I really want to emphasize that this is something that you need to be able to do even if you did not know the rule for the function f. In that case, you would interpret this as the area between the graph of f and the horizontal axis, the t-axis, from t is equal to 0 to t is equal to x, and look at those areas to complete this table, plot points, and then get the graph of g that way. And here we have the graph of g as sketched by Desmos, and you can see that it, of course, coincides with the graph that we got by plotting points. We'd like to conclude by considering a third function, and this function is h of x, and it is defined as follows. It is defined as the definite integral of f of t with respect to t from t is equal to 0 to t is equal to 3x. So the difference between the function g and the function h is that for the function g, the upper limit of integration was x, and for the function h, the upper limit of integration is a function of x. It is 3x. And what is it that we want to do here? We want to find h prime of 2. So to find h prime of 2, we need to begin by finding h prime of x. And we may do that by using the second fundamental theorem of calculus in conjunction with the chain rule, because the function h is a composition of two functions where the outside function is defined using a definite integral. So to find the derivative of the outside function, we would use the second fundamental theorem of calculus, and the inside function is 3x. So we need to use the chain rule. So h prime of x, using the second fundamental theorem of calculus, would be the integrand evaluated at the inside function 3x. So we're going to have f of 3x, and then multiply that by the derivative of the inside function 3x, which is 3. And of course, this is the second fundamental theorem of calculus that we just used. We also used the chain rule. Once you have h prime of x, you can find h prime of 2. So h prime of 2 would be equal to 3 times f of, replace the x here with 2, so you have f of 3 times 2, so that's f of 6. And you can find f of 6 by looking at the graph of f and going to t is equal to 6 and finding a point on the graph of f where t is 6 and figuring out what the y-coordinate of that point is. So it's just a matter of finding a point on the graph of f where the input is 6 and figuring out what the output is. For my graph, it's beyond the window settings of my graph, but I do have the function f here, so I can evaluate f at the input value of 6. So I'll have 6 squared is 36. 36 minus 1 is 35. So I have 3 times 35, and that is equal to 105, and that is the value of h prime of 2. So today we looked at our objective where, given a graph of a function f, you'll be able to sketch the graph of the function g that is defined as a definite integral using the function f as its integrand.